So it's my great pleasure to introduce Professor Jeremy Quastel from University of Toronto, who will be talking about KPZ equation in the universality class.
Okay, thanks. So I'm going to try to tell you this sort of story of KPZ. It's one of the big stories. There's a lot of different things. And I've been warned that none of you know it probably, so if you do, that's fine. If you don't, it's also fine. There's nothing particular I'm going to say with any problems with no either. This, what I'm going to talk about was really asymptotic probability until a few years ago. So it's all very new. There's not things which you were supposed to know or something like that. So just ask if there's any questions. So we talk about the KPZ equation. I'll show you the equation a bunch of times. So here's the equation. So the equation is an equation for a height function. H. It's evolving in t. X is just in the real time. Okay, so you can think of it as an evolving height function. That's what you think of it. That's why it's called h. And it's random. And it's evolving, mostly according to this heat equation. And then there's this non-linearity. So that's actually this is Berger's equation. Oh, integrated. And then there's this forcing. And the forcing is space-time white noise. See? Space-time. And I'll try to explain to you why it should be space-time white noise. I'm sure nobody knows what that is. Space-time white noise is a random field. It's extremely irregular. In fact, it's about as irregular as anything could be. What it means is that it's there's no correlation between the values at different points whatsoever. In a normal function, of course, the value here and the value here correlate with each other, so it needs to be a continuous function. But here, it's completely decorrelated. So the values at any two different points are completely, now that's a little bit cheating because they even have values. It's not a function, it's a distribution. And it's a horrible distribution. But if you integrate it over two patches, so you integrate it over a patch here and a patch here, what you would get is two Gaussian variables which are independent. So it's sort of independent stuff everywhere. And this corresponds to independent forcing. So what you've got is a either Berger's equation or a Hamilton-Jacobi equation being forced independently at different sites. Okay? And that's what makes these things go. And this is supposed to be a canonical model for stranded interface work. And it's got these three mechanisms which I'll go over again. There's these three basic things which are supposed to describe the attack of an interface moving from a metastable state into a stable state. Okay? And you can think of this height function. If you took a big piece of paper and you set it on fire on the bottom, and then there would be a sort of random piece of paper on fire, and then at a later time you have to sort of burn in front, moving up. Okay? And that would be KPZ. Well, there's tons of things, and I'll try to keep that. Okay, so it's a member of an enormous universality class of one-dimensional random growth models, randomly forced fluids. If you take the derivative, it's supposed to be the model of the one-dimensional randomly forced fluid. The edges of bacterial colony boundaries are supposed to evolve according to KPZ. Reaction diffusion equations, directed random fibers, which I might explain a little bit tomorrow. Anyway, there's an enormous number of things in this universality class, and are supposed to have the fluctuations which are given by this equation. So this equation describes dynamical fluctuations of coarse one-dimensional systems in a huge broad generality. And this universality class is sort of, well, colorists like to look for these universalities, and the ones you probably know of are things like the Gaussian universality class, where you know that if you take an average of a lot of independent random things, you get a Gaussian variable. That's the Gaussian universality class. That's such a limit there. That's one of the key things we know about the world. And this is an enormous universality class of non-Gaussian things. And this KPZ is supposed to be the canonical model. It's also fun from a point of view of analysis, because it's the simplest example of a real stochastic partial differential equation, which isn't trivial and which is susceptible to analysis. And here, a remarkable amount of analysis. Okay, so let's okay. So there's three basic mechanisms which go into these evolving height functions. Here you have a bunch of different models, some of which I'll describe in a minute. And you can see this random interface, and they're all supposed to be KPZ. If anything like this is supposed to be KPZ. Okay. So the three mechanisms are the following. So you're supposed to think of an interface which is evolving randomly like this. And there's three things. One, but the simplest one, is that there's something relaxing the thing, keeping it smooth as it can be. Right? And then there's this forcing term. And the forcing term, the space-time white noise, just basically says, I'm going to jiggle this thing randomly, independently at every point of space and time. Okay? And now one of the most important things is lateral growth mechanism. If you didn't have a lateral growth mechanism, then all this stuff would be just independently jiggling up and down. Just the last one to smooth it out, you have a linear equation, you can solve it, and you can calculate fluctuations fairly sure. But this lateral growth does everything. So the point is that these interfaces, there's no real frame in the problem. And so the interfaces grow out, not just up. Okay? And if you have something growing out, then the vertical part is some nonlinear function of the derivative. Right? Clearly things here where the derivative is big, they're growing much faster, right? So it's some nonlinear function of the derivative. Now, the physicist's idea is you take this nonlinear function and you expand it. Now, if you expand it, the first term, x0, that can just be removed from the equation by a simple shift. The second term can also be removed from the equation by a shift in this direction. So suddenly you discover the third term is the one you cannot remove by shifts, and they say, okay, now we discovered what the key parts are we throw over this, and that's the equation. So that's how they derive this equation. Okay. And in fact, the equation had been derived earlier in Kardar-Parisi-Zhang. It was called the stochastic Berger's equation. For some reason, we didn't get the credit. But it existed for that too. Okay. So now, here's a model. So here's the Eden model. This is a model of a bacterial colony. Okay. So you've got a lattice, which you can't see most of, except that the site at the origin is occupied. And now what you do is you add a neighboring site at random. And now you add a site on the boundary at random. And now you have another site at the boundary at random. So you just choose sites on the boundary at random. And if anybody's being careful, you might wonder what it means at random, because the corners count more than others. Well, there's different models depending on whether you say one or the other. And the point is you couldn't care less. It's not going to make any difference. All these things are very universal. So you keep adding them at random. Okay, and then you get this randomly evolving set. And that's called the Eden model. And that's a very, very simple model of how a bacterial colony grows.
Is the fact that it doesn't matter a theorem, or?
Nothing is known about the Eden model. Well, I'll tell you. There it goes, and that's what it looks like at some time later. Okay, so here's what it looks like. And the colors are just time slices of this thing. You can find pictures like this on the internet. Of course, it's a very simple thing for physicists to put on a computer, so they have lots of such pictures. But one thing that's known is that there's an asymptotic shape. So if you divide this thing by t, where t now just means the right thing to divide by, so that it becomes, as a fixed size, depending on how you put it. They're really an asymptotic shape, and it's known that on the two-dimensional normal square lattice, it's not a circle. That's known. So that's it. Let's do.
So this sounds rather unlike bacteria. The rate at which it grows is not proportional to the number of occupied sites, or you're saying addable.
You see, I can just speed it up. So that's speed. So that t is a little bit okay. let's make the radius grow at rate t and just add things so that it's doing that.
So you expect that it's harder for bacteria to appear in the interior than on the boundary.
Right, but the particular process he was describing did not seem to say that the number of squares you put down is proportional to the perimeter.
But none of this matters.
It's all just
the details. T is just the name for the radius, okay? It doesn't matter. And that shape, okay, maybe you can prove it exists. That's the state of things. But the important thing isn't that. The important thing is what are the fluctuations around. And why do I say that's important? Because those are universal. The shape will depend on what lattice you put it on. The shape will depend on what your growth rule is and all this silly stuff which it doesn't matter. But this chi, the growth exponent, and the actual distribution of the fluctuations are universal. So this is a universal thing you can say about the world. Like the Gaussian distribution. And it's really there. I was just thinking of this wall. If you were a little ant, and you started here, you see there's some randomness in the wall, right? If you started here and you went a distance t, there would be this random set. Now, you see these little random things are very, very small. But on a large scale, you would still see the same fluctuations as here. You really would. This is not proved. It's proved. I'm going to show you toy models like KPZ where it's proved. But in this one, it's totally over. And furthermore, we know what the fluctuations are. They're not completely universal. It depends on how you start that thing. So you see here it started with a seed in the middle. And then the fluctuations here are supposed to be the fluctuations you see from a random matrix chosen out of the Gaussian unitary ensemble. If you know what that is, if you don't, I'll show you what it is later. So you take the largest eigenvalue of a random matrix from the Gaussian unitary ensemble, and it has fluctuations which are the same as the fluctuations from the boundary there. And that's a little bit understood. What's not understood is if you took a half space, you could start this thing with half space too and let it develop, right? Then you would still see the same chi, this one 1/3. But the fluctuations would be different. They would be if you took them from a Gaussian orthogonal ensemble. And nobody knows why. Okay. Some of it can be proved, but nobody knows why. Okay. And this is one of the few things where there's experimental, there's a real experiment. This now is a liquid crystal. And what Takeuchi does is he fires, this thing's about 1 centimeter across, and he fires a laser beam in the center. Liquid crystal has two states, as you know. When you just look at your watch, there's a state which says the time and the state which is the background, right? So there's that state. This is the time, it's evolving, and then you measure the fluctuations. You measure the fluctuations starting from a seed, and he gets the unitary ensemble distributions. And from a line, actually what he does is he just takes the laser beam and puts it through a lens, so it fires a line. So these are these universal fluctuations that you're seeing that really appear in nature, and we are trying to understand with this KPZ. So let's go back to the KPZ equation. Okay. So actually, just going back, what the physicists would say is that the KPZ equation is an equation for this boundary here, evolving. Okay? Or an equation for this boundary here. Now that's a little bit weird because these things are not exactly height functions, right? So think of blue bubble. They're not that specific. So we're at a level of vagueness in this description that's beyond that. Okay, so you've got this KPZ equation. And now the KPZ equation itself, there's two big issues which are in some sense separate. There's analytic issues. And the analytic issue about the KPZ equation is that it makes no sense whatsoever. It does not, this is just ludicrous. You force this thing by this space-time white noise, and then if you drop this term, then you would discover that the solutions look like Brownian motions in space. Okay? It's not so hard to prove because you can actually solve it. It's linear. And then you take those Brownian motions and take their derivatives, which you're not allowed to do. So if anyone knows, Brownian motions know are differentiable. If you don't know, well, you can differentiate it, and the derivative is a spatial white noise. The spatial white noise is a horrible distribution. Now you're supposed to square it to try to make this equation work. It's just nonsense. It's clearly not okay. Okay. But actually, in this equation, there's an unbelievably weird way out, which is that if you do the hot-cold transformation, the hot-cold transformation is a transformation which takes the viscous-Burgers equation without the noise. Well, or you could take this thing to be a nice smooth function, and it turns it into this equation, which is the linear heat equation. Okay? So this if you don't worry that this thing is a horrible thing, not a function, then the log transformation called hot-cold just takes that formula into that thing to be linearized. Okay? If you didn't know it, now you know it. So if you ever see that equation, that's the thing to do. Now actually, this is again a problem because if you were going to try to do this, you would have to use Ito calculus to do that. And when you check the Ito calculus, you find out that the Ito correction term is infinity. So it doesn't work. Well, maybe it doesn't work. I don't know. So if you were to take this equation, and what I missed saying is that this equation is well posed. This turns out to be one of the very few stochastic partial differential equations which makes sense. So we just have to take that for granted. For some reason, and it is partly due to linearity, this guy makes sense. Okay? So you take this guy, and then you take the log, and then you get this funny infinity. So then the corresponding KPZ would have this minus infinity. So there's the KPZ equation we get. And the funny thing is that is the KPZ equation. So this is the actual KPZ equation. When you start doing some mathematical work on it, and I'll be a bit more precise about that later.
So H could, in a typical solution, be 0 or it could be negative in some place. You couldn't carry out this calculation in that region. But when
No, you have to worry that Z is the worry is that Z might be 0. So luckily there's a theorem you can prove a priori that solutions of this don't actually touch 0. And that's not easy to prove that it's true. Okay. Okay. H itself is just this, it could be negative or positive. Okay. So anyway, there's this minus infinity, which has to go in the, so this is an equation like a normal equation. It's a really crazy thing. Okay. So in general, what you mean by stochastic partial differential equation is a very odd object, which has only recently been made sense of in any sense. What you really mean is the following. What you really mean is that you should take your noise and smooth it out with some smoothing curve. Okay? So then you got a smooth version of your noise. You just solve your equation classically, and then remove the smoothing curve. And if, when you do that, you get a limit which doesn't depend on how you did this, how you regulate the equation, then you would say that's the solution of my stochastic partial differential equation. And for the stochastic heat equation, this works brilliantly, because it's nice and well posed. And now you take the log of it and the H epsilon, and now you just decree that this thing, the limit of it, well, the limit is just log of Z, and that's the solution. Okay? Now there's another complete side of the story, and I'll try to explain both in the next 45 minutes. And that's that there seems to be some exact solvability in this thing. So we've been able to compute some distributions in the KPZ equation, which is a very, very surprising thing. It surprised everybody. It surprised the physicists. And I'll just give it a flash.
Excuse me.
Yeah.
So the bottom equation, where you're subtracting the C of epsilon.
Yeah.
Do those individual terms in the right make sense, or do they only make sense in combination with each other?
Now in this equation, everything makes sense.
Well,
Let's
smooth
smooth out the
out.
noise.
Right.
Solve it. There's absolutely nothing.
But each of those things have a limit individually, or only when? Because I was worried about the dx squared.
That is exactly the right question, and I refuse to answer it. That's what Martin Harrer's regularity structures is doing. And I'll hint at it. I can't explain it. Yes. They all make sense in the right space, but that's not a simple place.
Can you make more comments about reversible unity?
Yeah, I'll try in a few minutes.
I mean, my comment is just Schrödinger equation.
Sorry?
The equation is just Schrödinger equation.
This is just a Schrödinger equation, yes.
So I mean, if you comment what you want to solve exactly.
I want to find out the distribution of Z.
Okay.
Z's a random object, and I want to know its distribution.
Okay.
Okay? And the more interesting question, because more interesting is the log of Z. I want to know the distribution of log of the first one is the log. But the interesting thing, as I was showing my case,
Even Schrödinger, there's a difference of a factor of odd, which is crucial, and it's unrelated.
well,
But that's what
okay, first of all, this is not your Schrödinger equation, because this C depends on T as well. It's not just the Schrödinger equation with the random
Close.
It's much worse. This depends on T as well. Okay? So if you want, it's a time-dependent Schrödinger equation, you're trying to find out the distribution of solutions. But here, you see, what you want is these very, very large scale. You want to now scale them out and look at extremely long scales and see this T to the 1/3 and then these funny random matrix fluctuations. Now how do you do that? So I'm going to try to show you there's some very, very special discretizations of this equation. Not the one I just showed you, not this Eden model. The Eden model, nobody knows anything what to do about it, but this one they do. So we know how to analyze the following model. And a couple of others, which are sort of like, this is maybe the simple as well. And it's called asymmetric simple exclusion. So in this model, you can think of it either as particles or a height function. The height function is the height function of KPZ, so it's a more natural thing to think about. The particles are what started the thing. So the map between particles and height function is very, very simple. If there's a particle, you have an up. And if there's no particle, you go down. So particles to height function. There's at most one particle per every site on Z. Okay? And the particles do some sort of random walks, and correspond to that, these height functions flip up and down. Right? And that's the whole thing. Okay, so the rule is the following. Each particle attempts to jump to the right at rate p and to the left at rate q, and p should not be equal to q or else it trivializes. And if it tries to jump on top of a particle and there's already a particle there, then it doesn't jump, and that's the end. It keeps running its clocks and sees when it can jump. Okay? Or in other words, see when this guy, suppose this guy at rate q it rings and he tries to jump there, then this guy here will flip to a, this thing will flip to an up, right? So let's just see that. So if you jump and there. That's the whole dynamic. So you can just think of little valleys flip at rate q to up, and up valleys flip at rate p to down, and that's the whole thing. It's a pretty simple model. And so this thing here you can think of as a random walk path. Random walk path just means a function which goes up and down by one at each step. Okay? And this is a dynamics, a Markov dynamics on random walk paths, which is you just take the down bits and flip them up at rate q, and the up bits and flip them down at rate p. And of course, if you've got a flat bit, nothing happens, right? If you're in a flat region, there's no up. If it does, it just waits till stuff comes in. And of course, now you can see that in the physicist's mind, this is just already KPZ because there's a nonlinear effect of the slope. See, the slope right here is 0. And there you've got some flipping going on. The slope right here is 1. And there you've got no flipping going on. So the function is just some discrete version of this nonlinear function. Okay? So this is a discretization of KPZ. And this discretization has some very, very special properties when Q is 0 or 1. It turns out that it can completely be solved by determinants, by simple transfer matrices. Okay. Okay, so this is what it looks like. This is just the same thing on a big scale. And now you're seeing this is what KPZ looks like. So this KPZ starts from flat. So flat here just means particle, no particle, particle, no particle, particle, no particle, which means a little wiggly version of the flat line. And now it's running, and you should sort of see that the thing is looking locally like a Brownian motion, but it still retains the flatness. And you can also see that it's not trivial. It's sort of, these things wander sideways because of this lateral motion, and that we can see that.
So the fact that it was moving upwards just illustrates time. It's nothing.
No, it's going up.
It is going up.
Because Q is bigger than P.
Are there more particles being created?
No.
Maybe I didn't understand the model.
No, because if the particles tend to move this way, then the thing tends to move up.
Mm-hmm.
Think about this. Forget the particles. Just think it's going up at rate Q and down at rate P. Q is bigger than P. So there's a tendency to move up. And in KPZ too, when I said the Briggs paper, the whole thing tends to move up or down. KPZ is like minus H also satisfies KPZ just with another sign on the nonlinearity, so either up or down, but it moves in one direction. Just like in the Eden model, the thing's going out. Okay? That's the up. So there's always going to be these huge constant things which you're going to have to subtract to see these fluctuations on top of them.
It's sort of a particle that's coming from the side of the screen. That's a good question.
No, I don't get it yet.
Do you want to watch the video again?
Actually, I have to go back to the picture with the particles and the.
Sure.
Understand it. There you go.
Okay. So here, forget the particles for a second. Just think.
Then he stops moving up and you're over at the.
This little valley is going to flip to this guy at rate Q. And this guy is going to flip to this guy at rate P. Q is bigger than P. Q is 3/4 and P is 1/4, say. Okay? So things are just dependent on that.
That part makes sense.
Okay, that's all it's saying. And in KPZ, it's the same sort of thing. The nonlinear term is assigned to the direction. Okay. Now, in this model, actually, a random walk is invariant. If you start with a random walk, then run the thing, later you'll see another random walk. But it's moved up. And in KPZ, Brownian motion is invariant. If you start the thing with a Brownian motion, and you wait, what you'll see is a new Brownian motion, but it's been shifted up. Of course, it's terribly correlated with the original Brownian motion, but it's still a Brownian motion. Okay, now, what we're interested in is these enormous large-scale behaviors, KPZ. And so to see that, the natural, simple thing to do is to rescale the height function and see what new equation it satisfies. Just the sort of first thing you would try. So we're going to look on some scale. Epsilon is going to be small. So epsilon is the ratio of the small of the bigger in the speed. And so we'll rescale space like this. And then, okay, corresponding to that, we'll rescale time by some epsilon to the minus z. Z is the scaling, dynamic scaling constant of this model, which we don't know what it is yet. And maybe we'll have to rescale the height by some epsilon to the b. Corresponding, and we'd sort of like to search for interesting b's and z's, which give you some interesting behavior. Okay. So if you do that, of course, it's fairly easy to take a PDE and rescale it and just see what new PDE it satisfies. And the only sort of tricky thing here is to rescale the white noise. White noise scales because the correlations are like a delta function, so it scales like the square root of the delta function. So you can easily check how it scales and you get this equation. Oh, sorry, you get this equation. Okay? And now you can look in here and see what should I do to get something interesting. Well, you see the heat would desperately like the Z to be 2 because that's the heat scale, right? But if I put Z equals 2, the nonlinear term is unbelievably unhappy because the it's not just that you should opportunity.
You divide by the e to the epsilon to the b throughout.
I'm just looking at it, it doesn't look right. It looks like there's a typo.
I think the last term should have epsilon to the minus b.
The last one?
Yeah.
No, I'm more worried about this one because if b is 0, z can't be 2. It wouldn't work. So there's something tiny bit wrong.
2z minus 2z instead of z.
Z 2 minus 2z there. Yeah, 2z instead of z. I can't do it in my head in front of everyone, but this one is like, that's really embarrassing. This one's right. I must have just written some typo there. This one's right, so we can easily check. If I take, there should be a 3 halves here. I think it just ruined my 3 halves instead of 2. That's all. This should say 3 halves. Oh, what? Okay. No, actually, yeah. Oh, yeah, okay, maybe it's right. Let's just take this.
If you differentiate z with respect to t, out for h epsilon comes out epsilon to the minus t. So when you flip that, it should have been a plus t.
But I know that if you take z equals 2, the first one's going to blow up badly. So okay. So, no, it's right, I'm sorry. Okay. Okay, let's go back. It's right. So, sorry about that. If you take, you see, you have to take b equals 2. A half. B equals a half. Why do you have to take b equals a half? You're trying to see something non-trivial. If you want to see something non-trivial and you start with a Brownian motion, then you're forced to take b equals a half, because even at time t equals 0, you've got a Brownian motion, and if you rescale it any other way, you're going to get some nonsense. Okay? So you're forced to take b equals a half. Now, once you're forced to take b equals a half, this guy wants z to be 2, but then here you get a minus a half. So you're in big trouble. Okay? So if you want to see something non-trivial, you simply can't rescale the thing to make the heat part happen. So that means that if you take b equals a half, which you're forced by the invariant measure, you have to take z equals 3 halves. to make this guy happy. But then this guy becomes small and this guy becomes small. And there's just nothing you can do about it, and that's just reality. Okay? So sorry about that. So you take b equals a half and z equals 3/2, and you get this equation, which appears that all this stuff's just going away, and you're going to the Invisible-Burgers equation. Well, the integral of the Invisible-Burgers equation. Okay. And so you say, well, as epsilon goes to 0, all the thing is just being governed by the Invisible-Burgers equation for this integral. But that's not true. That's not true because Brownian motion was invariant, and now you just check if the Brownian motion is invariant for the integral of the Invisible-Burgers equation, and it's false. So there's something very, very, very deep going on, and what happens is this guy doesn't go. It becomes something terribly interesting, which we don't quite know what it is. Okay. But what this does tell you, you see, at time t is this is the t now. The fluctuations epsilon to the b, which are epsilon to the 1/2, is t to the 1/3. So it already tells you why the fluctuations are of size t to the 1/3, and it also tells you that the spatial scale of fluctuations is t to the 2/3. So what it means is if you look at any of these problems, and it doesn't matter what problems, it's amazing, all these problems, if you look at time t, you're going to see fluctuations of size t to the 1/3 and on a spatial scale of t to the 2/3. Okay. Now the asymptotic fluctuations are not governed by KPZ, they're governed by the limit of this thing, whatever the heck it is, and that's something we call the KPZ fixed point. It's not governed by the limit. Okay, now, but there's something else you can do. There's something else, and that's called weakly asymmetric scale. So what does that mean? Well, the heat part desperately wanted Z to be 2. So if I put Z equals 2 here, then I get in big trouble because B is a half and I get epsilon to the minus a half, and that's terrible. It just looks like that's blowing up. But what if you started with something where you had an epsilon to the 1/2 here, and then you just did that? That's called weakly asymmetric scale. So you start with a model where it already has an epsilon to the 1/2 in front of the nonlinearity. And now you do the heat rescaling, which means to take b equals a half and z equals 2, and what you should get is KPZ. Does that make sense? So I start with something small, and that kills the problem of this blowing up. Now that sounds just like a complete mathematical cheat, but that is how KPZ arises. So, you take the model which I just showed you, this guy. And now what we're going to do is make the asymmetry be epsilon to the 1/2. The asymmetry is q minus p. So we'll take asymmetry to be epsilon to the 1/2, and then it looks like a KPZ with an epsilon to the 1/2 here. And now we'll just do this rescaling, and of course there's this big constant you have to subtract, but non-universal. You have to take this whole thing, just line up and lift it down, and eliminate you get this KPZ equation. Okay? So this makes sense. Okay. And this can actually be proved in this case. So in this case of ASAP, the one model I just showed you, this can actually be proved. And the reason it can be proved is because if you exponentiate the height function of ASAP, it magically satisfies a microscopic version of the Hopf-Bolt transformation, which is what took you to the stochastic heat equation I showed you before, the linear equation. So you get a kind of a linear equation for this, which you can prove goes to this Z, which was satisfying this nice well-closed equation. The only problem with this whole method is that it only works for this guy and one or two others. So we'd like to prove things converge to KPZ, but you don't have a tool to do it because the only tool you have is to hope for a miracle when you exponentiate it goes to the right thing. And so that's where Martin Heyer comes in. Okay. So this I'm going to try to explain to you because everybody's wondering what Martin Heyer won the Fields medal for. Okay. So we'll take KPZ itself, and you'll take a smooth approximation of the white noise. Now, if you have a smooth approximation of the white noise, of course, this equation is perfectly easily solvable. Then you put in some constant, depending on epsilon, and you know that this constant is going to have to be chosen carefully, and it's going to be big. And so his theorem is that there exists such a constant depending on epsilon, such that if you do this properly, these h epsilons, the solutions of this, actually converge to the law of equation. So that's Heyer's theorem. Okay?
And that's the same h epsilon that you scaled in the other page?
Yeah. And then anybody who was paying enough attention will say, oh yeah, but that's trivial. because all you do is take the H epsilon, and you take e to the H epsilon, and it exactly satisfies the stochastic heat equation with the C epsilon. And I just told you that that stochastic heat equation is nice, and so that thing converges down. Yeah, indeed it is trivial. So, but the thing is his method, not what he proved. What it proves, it doesn't depend on how you do this. So you could do some other regularization scheme. Suppose you wanted to regularize the equation. Instead of smoothing out the noise, you decide to put in a Biot-Classen simulator. Okay? Now, if you exponentiate it, it doesn't satisfy that stochastic heat equation at all. It satisfies some horrendous thing. And the method that I just showed you doesn't work at all. It's hopeless. So it still works. And it doesn't matter what you do. And it works not just for KPZ, it works for all sorts of stochastic KPZs. The only real condition is that these things should be what's called subcritical, which means, so they should be a parabolic type, which means that there's basically a heat equation plus some nonlinearities and then some noise. But they should be subcritical in the sense that if you zoom into the equation, which means you expand and look very, very tight into the thing, the nonlinearities get small instead of getting large. That's called subcritical. If the nonlinearities stay the same size, it's called critical. And what that means is that you can perturb off the linear equation and start trying to solve the perturbations of the linear equation. That's how the method works. But there's more. And this thing comes with a very powerful tool for controlling approximations. So, in particular, we can prove the following thing with Mark. Let's start with the problem we had at the very beginning. We're going to take, remember I said the nonlinear term, in principle, it should just be some function of the derivative. Why should it be quadratic? Well, it's quadratic because the physicist just expanded the function to second order and said, well, that's the first non-trivial thing you see. But in general, a random growth model, or a stochastic Hamilton-Jacobi equation, will just have some general function here. Okay? And now, you have to take it to be weakly asymmetric, and then do this heat scale. Okay? Now, for technical reason, and this comes from the method of Martin-Hare, the regularity structures, we have to take this thing to be a polynomial. It shouldn't matter. But unfortunately, I have to take it to be a polynomial. Okay, after 80 pages, I got tired, and I don't want it could be an odd polynomial. It's too much. So let's say it be an even polynomial. Anyway, that makes sense. You see, the function should be even physically, because why should it matter if you're looking this way or this way? So it would be very odd. Okay, now you rescale it. And of course, there's some constant you have to subtract, right? And then you do this, and you take the rescale, and then you make your thing. You get KPZ back. With the quadratic nonlinearity. Whatever you start with is f, it just becomes a quadratic nonlinearity. But it's even more amazing. The constant you get in front is not the constant that the physicist said it would be. It's not just the second derivative at zero. It's something much, much more sophisticated. Their expansion is nonsense. In a sense, it's true because the KPZ it is universal in this sense. So it's completely amazing. If you start, take f to be coordinate. Just f of u is u to the fourth power. And you try to make sense of the KPZ equation with the u to the fourth power. You just say, I'm going to try to make sense of it. So I'll smooth out the noise and take a look and see. Prove that there's a universal thing there. And, okay, just like you were supposed to do if it was a stochastic PD. So you do that, and the 4 becomes a 2. It just says, no, I'm not going to see you 4. We're going to do 2. And it's 6 times the xh squared. Okay.
You're saying this number lambda is always the same no matter what?
No, it depends on the f. It just doesn't depend on it that way.
But if f were x to the 4th, it would be 0.
No, it's 6.
Oh, it's not.
It's not that.
Do you know how it depends on the ages?
Yeah, anyone who wants, I can show them that.
It's a polynomial expression.
well. I mean, you can kind of, it's a Kirby polynomial with a certain background Gaussian. So let me just give you a picture of what's going on. So there's this world of models, not all of which I've described. You can look for some words here. The bacterial colony down using this Eden model. Richardson is just a version of the Eden model. Holistic aggregation, I didn't describe it. I can describe it now, actually. Holistic aggregation is you just let blocks fall from the sky. You've probably seen it on a computer. People make it called Tetris. So you have piles of blocks. And they fall down from the sky, and the rule is that when it falls here, it doesn't just suppose this is like that. The rule is instead of falling and just piling up here, they can stick to the side as well. Okay? So instead of just piling up, they'll stick to the guy beside. Okay? And if I'm not being very precise, it doesn't matter. Again. And this thing was also supposed to be KPZ. Again, anybody who wants to try? Anything you can prove. Doesn't matter if there's no result. It's nothing. It's zero. So there's a whole bunch of these models, these ASAPs, you've seen them. And then there's two scalings that I showed you on the last page. There's the true scaling where you go to the asymptotic world with these 3 halves and half. That's the true KPZ scaling. And then you see these wonderful universal distributions, some of which are coming from random matrix theory. And then there's this toy scaling, which I just showed you, is that some of these models have these adjustable nonlinearities in them. And with these adjustable nonlinearities, you can actually, you scale the model and it goes to the KPZ equation before it goes down to this universal fixed point. Okay, and that's what I just showed you. These are things we can actually prove now using this higher method to some extent. But these calculations, this KPZ fixed point, nobody has the slightst idea how to do these calculations, except by algebraic matrix, which I can show you. Okay. So now I'm going to show you some of this stuff. How did this KPZ fixed point is? This is an extremely non-trivial object. We don't know what it is, but we know some things about it, which I'll try to show you. And how we know this is an amazing story. So the story is because some of the models in the universality class have what's called a determinantal structure. And so one of those models, for example, is this ASAP when Q is equal to 1. The thing can actually be solved, and you can actually compute the height function in terms of certain matrix determinants. And now you do asymptotics on those matrix determinants, and this was a story which was going on throughout the last decade. Special names are people like Schwann and Johansen and Borden. And one can compute the asymptotic processes. So here, we take curved initial data. And then a picture has emerged of what's supposed to happen. So what's supposed to happen is you're supposed to see universal things, but it depends on the initial data, as I showed you at the beginning. You start with a seed, it's different from when you start with a line. Okay. So starting from a seed, you're starting from something curved. What you're supposed to see is what you would get if you started the stochastic heat equation from a delta function. And then if you take the log of the delta function, you don't know what to say, so physicists have a name for it. It's called narrow wedge. So narrow wedge is physicists' lingo for log of the delta function. Then the height function, and it's the height function on all these models, so that's this surface, is supposed to look like, well, it's growing, it has this growing thing, T. And then these curves, which are getting shallower, straight over T. On top of that, there are these universal fluctuations of size T to the 1/3. And in space, there's some very, very specific stochastic processes. These things called, this is a name, it's called Airy sub 2. That's called the Airy 2 process. That's a stochastic process, which its finite dimensional distributions are prescribed in terms of certain large determinants. Okay. So you're given a kernel, which comes from nobody knows where, from just the result of very explicit calculations. You take its Fredholm determinant on some extended L2 space, and that tells you what the finite dimensional marginals of the stochastic process are. So such processes are very strange. They never appeared before. If you've ever heard of determinable processes, that's something different. These are processes whose finite dimensional distributions are given to them. They're very universal. This governs the fluctuation. So literally, any problem I told you, like if you start on the blackboard and go out in those directions, that boundary fluctuation will be given by this area process. Whether we can prove this, God knows. Okay. And then if it's flat, there's just another area process for it. It's T plus some other area process. And the picture I showed you at the beginning, the movie, what you were seeing was a picture of this area process. This area 1 process here. And these numbers 1 and 2 come from random metrics that we don't really like. Okay? And of course the spatial scale is this T to the 2/5. That's the scale on which you see these things before. If you look at a smaller scale, you can see the thing already looking Brownian. So all these area processes are locally looking like Brownian motions, but then they have correlations on larger scales, so that the area 1 process, for example, can sort of appear flat, but locally like a Brownian motion. Now, the big breakthrough was an amazing formula of tracing the limit. This formula is a miracle formula. It had no right to exist. It's an exact formula for the probability distribution of the A sub height function. That's the exact one I showed you in the little movie. Not in the movie, because the movie was starting from a different boundary condition. So here we're going to start from all the particles on one side. Okay? So all the particles on one side. So initially the height function looks like a big V. And now you'll run it, and it'll start, after a while, it'll start to look like, so you start with a height function like this. And so, of course, the first move is obvious, because like this, right? And then it starts to run again. And after a while, you'll see something that sort of looks like this. Okay? And now, this is an exact formula. You take one point, you fix a time later, and you take one position, x, and then you look at the distribution there. You're looking at the random distribution that you get there. And you have an exact formula. And this was something that was completely unexpected, that there's an exact formula. Of course, the main thing you're taking out of this thing, the formula is extremely complicated. There's no doubt that the formula is complicated. But that the formula exists is already a miracle. It's an integral of some crazy functions against the Fredholm determinant of some very, very strange operators. And it takes a few lines to write down. But the key points are that the process does not have a determinantal structure, so it was a surprise. The determinant in there is just a plain surprise. It's just, God knows why they even try. It's done by solving certain n-particle problems using things called data ansatz and then extending out and just sort of suddenly seeing these determinants. These kind of formulas only exist for very, very special initial data. Very special initial data, suddenly you get amazing formulas. Nobody quite knows why. And now you can take this formula, and as I told you, you can rescale this ASAP using this weakly asymmetric scaling and get this KPZ, right? So you plug in that rescaling, then you'll get a formula for KPZ. So all you have to do is take the limit of this formula, plugging in that rescaling. So you take this formula, you plug in that rescaling, you calculate for 1 year, and you get this formula. And it was done by 2 groups independently, Quastel and Squad and us independently. It took both of us exactly a year to do the calculation. The calculation was redone by physicists about 3 weeks later, using some non-rigorous methods. And you get an exact formula for KPZ at a fixed time instead. So you're solving KPZ here with this narrow wedge initial data, which means you take the stochastic equation, start with the delta function. You wait till time t, you look at position x, and now you have an exact formula for the fluctuations. It's a very strange formula. It's in terms of a very oddball generating function. But the generating function determines the distribution, and you get something in terms of a Fredholm determinant of a fairly simple kernel. And in the limit of this kernel, in the limit as t goes to infinity, you're supposed to see these GUE fluctuations, and indeed you see exactly that, just by taking the limit of this formula. And here I've written down what the GUE is. No, a GUE matrix just means I have a matrix which is Hermitian, full of normals, independent normals to the extent you could. And now you take the largest eigenvalue of that, and it scales exactly the same way. This n is corresponds to t, and you get n to the 1/3, and you get this very, very strange distribution, the Tracy-Whittem distribution. For the, so this Tracy-Whittem distribution has been coming up in all sorts of problems. And why it comes up here took an enormous research effort to understand. There's a picture of them. So the physicists put it on the computer, and it starts out with this normal distribution, and then as time goes on, it evolves according to this green thing, which is the GUE Tracy-Whittem distribution. And of course, the sort of sad thing is that all probability densities kind of look the same. Because you don't really see much here except this rather odd wandering of the center, which it does actually non-monotonically go to this, which is very weird. That has been explained by physicists. The Tracy-Whittem, of course, the Gaussian looks like e to the minus x squared. This guy looks like e to the minus x to the 3/2 here, and e to the minus x cubed here. I don't know if anybody can see that with their eye, but it really is different. And then that started off a little war where mathematicians and physicists tried to get formulas for different initial conditions, and actually you can see something rather odd, because usually, physicists discover things that a mathematician go on and prove out, epsilons and deltas. So now this formula, which is perhaps the most important, was discovered by us first with a rigorous proof. The Sassamon response proof isn't rigorous, but it's basically just a non-rigorous version of our proof. They were doing the same thing, they're just physicists, so they didn't write down anything carefully. And then followed by a very non-rigorous proof a month later. And then Ivan Corin and I got this half-Brownian means just sort of one size motion. And then you get another formula of the same nature, followed up by a non-rigorous proof a year later. You sort of wonder what this is having in mind, right? Giving non-rigorous proofs of things which have rigorous proofs, but then they start to win. And the reason they start to win is because what they do is they have extremely non-rigorous arguments, but what they can do, because they know, they sort of follow they calculate until they say, oh, this is the right thing to get what they got. And now I know what I'm supposed to do here. And so now they start doing it in other models where we can't actually do it. And it took a long time, it took 2 years before their rigorous proof actually came with this Brownian initially. So that is, you start with a two-sided Brownian motion, and now you actually get the whole distribution at one time. So that is just finally been proved. Actually, it's a bit complicated. It is not known whether their formula is their formula. There is a rigorous formula, and there's a non-rigorous formula at this stage. And
So these are the same techniques that led to the long computation of lambda, or that?
No. This is much more complicated. In fact, I'm actually going to show you how to do it. I have enough time. When does it end?
An hour after you began.
Okay. Then I have enough time. I'll actually show you what they're doing. Okay. And then, okay, so they're getting this out. Fine. Flat is very, very, very difficult. This Brock is very, very difficult to do the computation and completely unexplained. You get this GOE Tracy-Whittem distribution, and although there's been an enormous effort, this Alexei Borgen has an enormous program which has basically explained why you get the FGUE distribution in the curved case. It has absolutely nothing to say about the flat case. And nobody really knows why. So here's what physicists are doing. Just for fun. It's fun to see what physicists are doing. I don't show you one of our proofs. I'll show you the nonsense proofs. Okay. Okay, so the whole reason that KPZ is solvable is there is something computable. And then in our cases, what we're doing is we're doing rigorous versions of this in a way. It took a long time to understand this, but now we can make it like that. Okay. So if you take products of this Z, remember the Z is this this e to the KPZ, and it's supposed to satisfy the stochastic heat equation, so maybe I'll just write it on below. So it's dTz equal to Px over Z plus C. This is space-time white noise. And then there's an amazing fact, which is that if you take the z's and take them at in different points, take the product, and then take the expectation, so that just gives you a function ut x1 for xn, and that actually satisfies a closed equation. And that closed equation is called the delta Bose gas. So it satisfies dT du equals basically a heat equation plus the sum of Diracs at the diagonals. Okay? And this isn't exactly, you can make mathematics of what it means to have Dirac potentials, so don't worry about that too much. Now, the thing about that is that this thing has a long history, this delta Bose gas. So if the sign here was negative, this was already solved by Lee and Lineker in the late 60s. Solved means compute the eigenfunctions and eigenvalues. Okay? The plus is a lot harder, but the eigenfunctions and eigenvalues are known. And in fact, this has a big history in representation theory, and there's famous papers in algebra. Heckman and Altman have extremely interesting formulas for moments of these things, etc., etc. So this thing now ties into a huge area of mathematics and representation theory. Okay, so the main thing is this thing is exactly solvable. And that means you can compute U. You can compute U by an eigenfunction expansion. So you just start with your initial data and you compute U. Okay? The problem is that the answer is really complicated. The answer is just an enormous sum, and these eigenfunctions are, well, you were told in school the eigenfunctions are E1, E2, E3, E4, but the parameters on these eigenfunctions aren't 1, 2, 3, 4. They take values in some very, very strange space, and now you have to sum over that space, and summation cannot be performed. Except in a few special cases where there's some magic combinatorial identities and you're able to perform the summation. Now, what this is doing is, once you compute these things, and maybe you have some magic formula which allows you to actually perform the summation, and that's why ours work too. But then what they do is they say, okay, now I've got the moments, because I could just take all the x to be the same, so I got the moments. And I'll take the moments and I'll reconstruct the distribution out of them, and that's great, and perfect, except that the moments grow like u to the n cubed. And there must be some analysts in the audience who know what happens. Well, if you want to construct a probability distribution out of its moments, they better not grow faster than about e to the n. Otherwise, it's false. It's just false. It's completely false. There's not just one counter. It's just completely false. This does not in any sense determine the distribution. So, and of course what they're seeing, what that tells you is some tails of the distribution. And in fact, if you just check the traceability distribution, the tails grow exactly like that. So what they're seeing is some very, very high fluctuations of the okay, but this is, they have their methods, and this is called the replica trick. So what they do is, these things are called replicas, and you can just make this series, and this series, well, that series should represent this. And Z's a positive object. So this guy does actually determine the distribution function. This is just the generating function of the Z. So you can keep the generating function out of the moments. The other problem, of course, is this series is u to the n cubed. It's ridiculously divergent. So what they're doing is they're just writing down divergent series like this, and then resumming them. And resumming divergent series is a real problem. But, of course, if somebody told you the answer, and you just manipulated the divergent series until you get their answer. Right? And now you get to do the next problem, and you say, well, even if they don't know the answer, I'll just manipulate it the same way, and I'll guess the answer. That's what this is doing. So that's basically the way the thing stands. We have one-point distributions in a number of cases, and that tells you something about this KPZ fixed point, but not certainly as much as you'd like. And I'll stop.